Now, what is actually runtime and training time complexity and space complexity for the decision tree? So let's see. So first we will discuss the time complexity. When you training the decision tree, then how much time it will take? Let's see first. First see the training time complexity. So it's it's approximate equals to order of n log n d, n log n d. Okay, we will see this thing, why actually it's training time complexity order of log n d. We will see this thing where n is equals to, here actual n is equals to number of data points in the training data set, number of points in the training data sets, and here d is equals to dimensions of the features vector, dimension of the features vector. Okay, so but the thing is that you can easily ask, sir, when we will take on the numerical features, then we will see there have the category, the threshold value of the numerical features is so large. So in such cases we will increase the time complexity. It may take the, yes, obviously it may takes the time complexity, but there happen algorithmic methods. How? Let's see how this. Suppose let's take, we have a numerical features. Suppose let's see, we have a numerical features. Okay, and for these numerical features, there have, suppose we have numerical features, suppose there have the threshold value for these numerical features also large. The threshold value, for this numerical features also large. Okay, so but the algorithmic method is that we already know, we have known that for a sorting technique how much time we will take. For a sorting of a data, we will take the n log n time. For sorting any kind of data, we will take this much time. So here you will see this thing, n log n. This is responsible for sorting the data. We will see when we will discuss the numerical features, how to handle the numerical features for the decisions. We will see this thing first step we have to sorting this numerical data. Then after that, we have to find the threshold value. Okay, and according to the threshold value we have to calculate the information gain, and according to the maximum information gain we have to choose the which threshold value we have to use to splitting the data. Okay, this thing already we have seen in this chapter, in this lecture, numerical features lecture. Okay, so here first we have to, just this thing is actually responsible for sorting the data. Because of that, because of, just I am writing this time complexity because of, first for numerical, just I am considering the worst case only. Okay, the numerical features, this is the worst case only happen, we have taken the numerical features. But if we taken the categorical features, there are no matter, there have fewer kind of category for a categorical features we have seen. And I will also since if we have a large number of category for a categorical features, we have to convert these features to a numerical feature. So we are considering here for worst case a numerical features. Okay, so this log n is responsible for sorting the data, and this d value means dimension of the features vector. Okay, this is responsible for the evolutions. Actually what we are doing in every step, for every features vector we have to calculate the information value. If we calculated the information gain value, then we have to calculate the Gini impurity or the Gini impurity or then we have to calculate the evolute, when we evaluate the information gain, then we have calculated the Gini impurity or the entropy value. Okay, for calculating this we have to find the entropy value or Gini impurity value, Ig. Okay, so just we will see this d is for responsible for that. for age features corresponding to age features. So because of that we have multiply here d. Okay, for calculating the information's gain, for calculating the information scale. So this n log n is responsible for sorting the whole numerical features data, and this d is responsible for calculating the information gain value. Because of that, in training time its time complexity is n log n. Okay, the main issue is that here if we have a data, suppose if we had a data, suppose let's take the in our data d is very large. Suppose let's take in our data d is very large. So in such scenario, if our dimensions of a data is very large, in such scenario we will omit this decision tree because of its time complexity. Actually in a data sets n is large, also n is large, but as well our dimensions is also large, then large into large also very large. Okay, so because of this reason, because of this is also a very large, so we can avoid this thing. We have not used this decision tree for a large data set. Okay, now let's see when we have the runtime complexity. When we running the after training, when we run this model, then how much time and space actually we need. We need to find what we are doing in runtime. So actually in runtime we have a query point, and we have to find its class level or its output corresponding to this query point. Okay, this job we have to do in runtime. So first let's see in runtime what is the actually space complexity. In runtime, what is space complexity? Let's see it first. So the space complexity is nothing. First, space complexity means we have to store the whole data. So data means whole tree. First, in the space complexity, we have to store the decision tree. Okay, and the decisions means what? How much space we have taken to store this decision tree. Decision tree means actually we have a if else condition, nested if else conditions. Okay, means we have a if else like that. If else like that means we have actually we have to store a nested if else condition. Okay, if we store this if else condition, then how much time actually how much space we taken. So the space actually taken to store these if else conditions means the number of nodes that we have. Number of nodes plus means number of internal nodes as well as number of leaf nodes. This is the total number of nodes. Plus number of leaf node. That much space we have to store the whole decision tree. So this is the simple space complexity at runtime. Okay, so but typically we have built, just in the previous lecture we have seen when we have tuning the hyperparameter, we have taken a medium number of depth for a tree, because to avoid the overfitting. Okay, average number of depth we have taken. In generally the depth are taken in generally the depth is considerable, is 5 or 10 in most cases. For a decision tree the depth is taken 5 or 10 typically. typically we use this depth for a decision tree. Okay, but if we just one thing, if we just increase the depth, what happen? If we just increase the depth, then what happened? Then if we increase the depth, means we have increasing increase the number of loops. If a nested if loops conditions we have increased, if we increased the number of nested if else loops, means what? We have increased the number of internal nodes. If we increase the number of internal nodes, means what? We have increased the number of hyperplanes for our whole space. So in such cases, our interpretability for our model is decreased. Your interpretability of the model are decreased. Okay, in such cases. So the thing is that we have in runtime how much space that will see. The space is we have to actually needed the number of internal nodes plus number of leaf nodes. Now how much time actually need in runtime? Now let's see. So at runtime, how much time actually we need? Now let's see the time, how much time we need. So the time actually we need for calculating, suppose let's draw a tree. Suppose let's take it's our tree. Okay, suppose let's take, so to evaluate it, suppose let's take we are a query point we have. Suppose let's take we have a query point xq, then we have to finding its corresponding out level. So what we have to do, we have to first check this condition, next we have to check this condition, next this condition or this condition. So maximum the checking conditions is what? So the number of maximum checking conditions, the maximum depth of the any node, any leafed node. Okay, so the maximum, suppose the maximum number. So the in worst cases, how much time it will take? If we our query point, if we coming here for the, if our conditions is fulfilled and coming here, then it's okay. In this step we have taken a decisions, it's the best case. But if we consider the worst case, what happened? First we have to check this condition, this condition, then this condition, then this condition, then we have reaching here, then we have taken a decisions about the output of this query point. So in such scenario, we have to travel this amount, this route. First we have to travel this route, then this route, then this route, then this route. Okay, so this is means the maximum depth of any leaf node. So the depth, we have to table the depth of the, so to find the time complexity, if we taken the depth is k, so this k will be maximum depth of any leaf node. This much time we have taken at almost we need this much time we need to take. Okay, so if we just conclude this lecture, for a decision tree, what we will see, for a decision tree, decision tree is always better for a large data, for a large set of data and a small dimension, and if our dimension is small, because if our dimension is large, then we in training time complexity is so large. Because of that, we have not used the decision tree for a large dimensional data. But if your if our data set is large but the dimension is small, then we can easily consider decision tree, and it is the one advantage. The another advantage for decision tree is that, if we interest to build a low latency model, then simple, just for runtime complexity, you will see the runtime complexity is simple order of the depth of the tree, order of the depth of the tree. And in generally we have seen for a binary tree the depth of the tree is order of log n. Okay, in binary tree consider, but it is not a binary tree. In such scenario the depth of the tree also low for binary depth for binary decision tree. Okay, so just see, because of this, if we just simply, because of its low latency at runtime, because of its depth, order of the depth at runtime it will take, so we can easily build a low latency model for a large data set and a small dimension. If our data set small dimension is for a data set is small, and number of data sets for a model is so large, then we can easily build a low latency model. And this thing is very useful. If you just see in a popular internet website, popular internet applications, internet application decisions is very useful because of its low latency. Because of its low latency, it's very useful because of its low latency. Okay, and also Amazon's, Flipkart, Google, as well as some famous internet company used this decision tree. And also in the next chapter we will see, it's some extension of this decision tree that we'll call a random forest, gradient boost decision tree, that we have seen in the next series of lectures. Okay, I think the time complexity and space complexity, and why it is useful, what is actually advantage, what is actually disadvantage, when we have to use this, when we have to not use this. So I think these questions is clear from these lectures. So I am again repeating this thing, so that this decision tree is based for a large data set. If its dimension is low, then it's the appropriate model to use it. And another language, if we have a large data set and we are interested to build a low latency model, then this is the proper one. Okay, and for a large dimensional of data sets, we can neglect this thing, this dimension, this decision tree. Okay, I think this is the it's the bad side, and this, if for a large dimensional data sets, this is the bad side, and for a low dimensional data sets it's a good side. Okay, this is the more advantage and disadvantage for a decision tree.